Welcome to Topic 3. I'm going to be reviewing a little bit of the information that we covered earlier and getting into a little more detail about it as we continue our march toward inferential statistics. We're going to get into a little more detail about significance, type 1 and type 2 error. Again, mention how this impacts inferential statistics, confidence intervals that you had a little bit of practice with in Topic 2, and calculating a one-sample z-test, but we're going to show you how to do that in SPSS in this particular video. And this video will go a little longer, but you might want to get some pencil and paper and make a few notes as we go. So, in review, we learned the importance and how to conduct some simple descriptive statistical analysis using SPSS and draw some conclusions based on the numbers that we generate and the graphs that we generate. We have learned to find relationships between variables in our sample and those in the larger population by comparing our sample numbers to the normal distribution curve. And then we will go further by conducting some of the inferential statistics where we compare our data that we calculate to the larger unknown population. And you can do that with a true experiment, which is also known as a randomized controlled trial, or a quasi-experimental, which would be a non-randomized and less robust statistical test. So in review, we learned that the basis of all statistics is really the ratio of effect over error. We learned how to take a sample and measure the central tendency and variability of that sample, how to generate and display those descriptives using SPSS and handle outliers and missing data. We also learned the tools for looking at validity and reliability and how to reduce that as much as possible so that we can reduce error. We learned how to ascribe levels of measurement to variables. We know, for example, that nominal level data are categorical, they're not related, such as blood types, colors of cars, grades in school, gender, race, etc. We learned how to properly categorize ordinal data, which would be a rank, much like a Likert scale on, say, a test where we are asked to agree, strongly disagree, or that type of data. Interval and ratio data generally considered together, but we talked about how that's the strongest type of measure, of level of measurement, and that would be things like weight and temperature and blood pressure, where you have continuous data. We also learned to distinguish between an independent and dependent variable, which again is going to be important as we march toward these more robust statistical tests. We learned how to correlate variables and look at linear models to show strength, direction, and significance of a correlation. And we learned how to compute a z-score, how a person's individual raw score would rank in the sample. And we can compare that to a normal curve because of the central limit theorem. We also learned how to write a hypothesis, both the research and the null. We also learned how to write a directional or non-directional hypothesis so that we would know whether or not to use a one-tail test or a two-tail test in looking at our results. So we're going to look a little more at significance. Significance is defined as the result of an inferential statistical test is due to a specific influence, maybe the intervention that we chose, or is it due to chance? So if our observed score falls in either region of the normal distribution curve, as you see here in the diagram, then we can reject the null. We know that that our sample for this particular variable is not likely to chance. Perhaps there's some reason, maybe it's our intervention, that our group is different from what we would expect in the normal curve. So how do we do this? We convert a raw score to a standard score, and we can that score might be a Z-score or a T-score or an F-score that we'll learn about later, and then we determine where it falls on the normal distribution. If our observed score is greater than the expected value, our results are significant. We can reject the null because it falls in that critical region outside the area of the tails of the normal curve. Statistical significance tells us if our sample model can be inferred to the larger unknown population. It's reported as probability. If alpha priori is set at 0.05, there's a 5% chance that the sample result that we calculated occurred by chance alone. There is a 1 in 20 chance that we are wrong. But still, we can, since we set that as our probability, we're pretty sure that our result is significant. So here's the crucial point. Testing statistical significance is all about the likelihood of a chance finding that will not hold up in future replications. Significance does not tell us directly how big the difference was. So I want you to understand that just because we get a significant p-value does not mean that our results can be taken to the bank with future tests. So I want you to turn up your speakers. We're about to watch a humorous explanation of why statistical significance is not always significant.
Princess Elizabeth of Dementia was, as all proper princesses should be, pretty hard to please. She was also very good at maths. Her father, King Rupert, had promised her hand in marriage to anyone who could come up with a proven treatment for his elder subjects who were suffering from mild memory problems. The truth is, he was pretty confident that no one would be able to do it to her satisfaction, and that his daughter would remain unmarried and able to look after him for many years to come. Prince Robert of Concordia was very keen to try his luck with King Rupert's challenge, and consulted with his nutritional advisor about how to go about it. Well, since you asked, Prince Robert, I've heard on the grapevine that anything containing polyphenols is great for your memory. As it so happens, I've got a job lot of grape juice in the back of the van, which is full of them, and I really need to shift it. The thing is, the expiry date is in 12 weeks' time. If you get a move on and do a try on some elders as soon as possible, I get rid of it, you get the girl, and King Rupert will place a massive order of grape juice for all his older subjects. Everyone wins. You've just got to get a bit of evidence that it works.
That's quite a tight timeline to do a trial. And what if it doesn't show any benefit?
Well, you know what they say about statistics. We'll cross that bridge when we come to it. Just get recruiting, make sure you randomise, double-blind, all that rubbish they love at Castle Cochrane. Job done. And if it doesn't show any benefit, I've got a cousin at the Blueberry Marketing Board who might be able to help you out. Anyway, hurry up, this trial isn't going to run itself. So Prince Robert proclaimed throughout the land of Concordia by email and Twitter that he was running a randomised controlled trial on grape juice to improve memory, and he needed elders with mild memory problems to sign up by 3 o'clock that very afternoon. Unfortunately, only 12 subjects got the message on time and fulfilled the eligibility criteria. But Prince Robert was so desperate to win the princess, he ran the trial anyway. After a few short weeks, the trial was finished, the statistical analysis was done, and the report had been written up on a beautiful scroll for presentation to the princess. Prince Robert was feeling quite pleased with himself as he hopped through the gates of Castle Cochrane with the scroll under his arm. With a great flourish, he presented the scroll to the princess. She opened it and read the title.
Concord grape juice supplementation improves memory function in older adults with mild cognitive impairment. Promising title. Let me have a closer look at the numbers. Oh, will that really be necessary, Princess? You can see from figure 1 that on average the elders drinking grape juice remembered 5.4 more items than the control group of elders drinking fake grape juice. And the p-value of 0.04 says it all. It's a significant result, no doubt about it.
Let's get hitched, please.
I find table 1 a bit more revealing. Corby are old-fashioned, but the placebo group scored a bit lower on all the cognitive tests before the trial even started. So isn't the graph a bit less misleading? Shouldn't it show the relative difference between the two groups, which was 3.4, not 5.4?
Well, I suppose you've got a point, but whatever you think about the graph, the statistical analysis shows there's a significant moderate positive effect of grape juice on memory.
For list acquisition, but not delayed verbal recall or spatial memory.
I gotta say, 1 out of 3 ain't bad.
So you'd say grape juice was definitely worth drinking if you need to remember lists?
Definitely. You've got to admit that a p-value of 0.04 is impressively tiny. There's only a 4% chance that the improvement in list learning was nothing to do with grape juice.
Oh yes. The very small p is obviously great on remembering listing, but I really think we should have a closer look at the other aspects of the trial design.
Honestly.
Yes, I think we really must. Daddy would be awfully cross if I didn't look at the evidence properly and married the wrong person. Gosh, it says here that your study only had 12 people in it, and only 5 actually drank the grape juice. Couldn't you have rustled up a few more elders? Personally, I wouldn't get out of bed for less than 60 participants.
Oh yeah, we didn't have a whole lot of funding and we were a bit pushed for time. It's a preliminary study anyway. It was randomised and blinded, so that's good, isn't it?
Randomising 12 whole people! You must be exhausted. You've done an awful lot of statistics for just 12 people. Isn't it a bit over the top, is it?
Well, yeah, but we've just got this great new software at the Palace. You just plug the numbers in. Well, actually, you do get the servers to plug the numbers in. And then, bingo! Out come teeny little p-values of 0.05 or under. So sweet. It's like magic, really. But anyway, you don't need to worry your pretty little head about how we analyse the results. A p-value of 0.04 tells you the result is statistically significant. Oh, that's all you need to know. Isn't statistics wonderful? All the newspapers are going to love it. Ka-ching.
Can I make a suggestion on a better way to detect whether grape juice actually has a significant positive effects on memory or not, and increase the probability of me marrying you slightly from the current p-value of
0.00000001? Sure thing, sweetie. Go right ahead.
It's not rocket science.
Well, yeah, as I say, we didn't have time or much money, and, well, we didn't have,
Tell you what, why don't I have a little look at the raw data? I love data. I'm not sure these software packages give a very clear picture half the time.
Well, there might be a little bit of a problem with you seeing the data.
Why is that then?
The Palace server crashed. And, we fixed it all. Good thing I wrote it up on this lovely scroll, isn't it?
Really? So you're telling me, on top of everything, if my friend here at Castle Cochrane wanted to write a systematic review on meta-analysis of trials on grape juice for memory, they wouldn't be able to include the raw data from your study because they're now unobtainable?
Yeah, I guess so.
It's hardly a great basis for marriage into the Cochrane royal family, is it? Now I'm rather busy. I have to finish a very important paper on reporting standards in trials of diagnostic test accuracy.
I'll get my coat.
Statistical significance can be quite misleading, as you just saw in the Princess and the P-value skit. First of all, we can have error due to sampling problems. Self-selection bias is one. Remember, the frog asked for anyone to participate? There was no confirmed diagnosis of memory loss. There was really lack of randomization. Not controlling for confounders. For example, what if the subjects in the Princess and the Pea study were on medications to improve their memory? Or what if they had other diagnoses that impact memory, such as history of a stroke? A small sample size also contributes to error. Remember that magic number of 30? The Princess wanted at least 60 in the group, 30 in the control and 30 in the experimental. We need this many to use robust statistical tests. Another type of contribution to error in statistical significance is the intervention. In our little Princess and P-value skit, they used grape juice. But how much of that liquid was actually grape juice? Was there an exact polyphenol amount known? What is a sufficient dose to be effective on memory loss? And how long does it need to be consumed before the results can be effectively measured? Are there conditions that would impact polyphenol activity? What is the metabolic basis for the effectiveness of polyphenols on cognition? Were the subjects consuming polyphenols from other foods in their diets besides just the grape juice? What memory measurement tool was used? Was it reliable and valid in this population and under those conditions? What was the education level of the subjects? What about IQ? Would that impact the ability to remember facts? As you can see, this study would have been torn apart by a Cochrane reviewer who would be looking at the intervention and all the confounders that would impact that intervention. A third and major consideration when looking at statistical results is the statistics and the impact of sample size on that. There needed to really be 3 groups for comparison. In that group they had a placebo and a treatment, but we really needed a no treatment group. This is often a serious problem in many of the tests that are conducted where people loudly proclaim they have statistical significance, but they haven't really compared it to no treatment at all. This is a very famous photo that illustrates what we've been talking about. It's an example of sampling error. Selective heavier polling of Republicans led editors of Republican leaning in the 1940s, the Chicago Tribune, to release early editions of the newspaper showing Dewey won the 1948 presidential election when in fact he did not. The Tribune quickly released a new paper in moments following election results, but someone found one of those early 100,000 copies and provided one to Truman 2 days after the election when this photo was taken. It's beyond the scope of this course to define all of the sampling methods, but students should know that there are different types of sampling methods available. Most outcomes research projects use convenience samples. We have a group of people and we measure the variable of interest in that group because in the clinical setting, it's not always feasible or ethical to randomize people to a treatment or a non-treatment group. There is bias in this type of sampling method. One type of bias that must be avoided if possible is called self-selection bias mentioned earlier in the Princess and the P-value. Remember, he asked anyone in the kingdom who would like to participate to come forward. Imagine that asking for everyone in a company who is obese if they'd like to participate in a research study on quality of life and obesity. I suspect you would not get a fair sampling, as people are reluctant to step forward and participate by identifying themselves as obese. Random selection assures that every potential subject in the population has an equal chance of being selected. This means that the sampling is free from bias. What I'd like to do now is show you how to use a random number table when you are truly randomizing subjects into a study.
Okay, today let's figure out how to pick random numbers. It's not complicated at all, and let me show you how. There's two ways to do it. You can let a computer do it, or you can get it from a table. Computers do it for you all the time. You can get calculators with an R&D button, or if you ever play slot machines, the new electronic ones, they're just big random number generators is what they are. But let's try and get it from a table. Now, your procedure is as follows. You take your finger, kind of close your eyes, and you roll your finger over the whole table, and you let it drop somewhere in this table. We're picking numbers from 1 to 75. At least that's what we're going to try to do. Let's say we ended up right there. Okay, so you fell on that 2. Since we're picking numbers from 1 to 75, we'll pick them 2 at a time. That means your first number is 25. Then go over to the next number in your table, which would be the 07. The next number is 07. All well and good. The next one, you'll have to go over a couple of columns. You get an 8 and an 8. Can't use it. It's too big. We only wanted numbers from 1 to 75, as you see here. So we skip 88. The next one over is 61. Let's put that down. Your next one would be 29. Let's put that down. Now your next one, if you kept going, is 61. Can we use a duplicate? It all depends if you're picking with replacement or without replacement. With replacement means you pick a number out of a bowl, you look at it, and then you throw the number back in the bowl, and you could pick the same number again. If we're picking with replacement, we would accept the 61. If we're picking without replacement, we'd have to go on to the next number, which in this case is 49. And that's how you pick random numbers.
So that's hopefully demystifies a random number table for you. A less laborious method is systematic sampling. If we wanted 100 people from a population of 1,000, we would just pick every 10th case. There's also stratified random sampling. That's useful when we want to have a fair representation from subgroups in a population. Let's say that we wanted to assure that we select equal numbers from every race or from every year, depending on what the variable that we're looking at. Or maybe we want to get subjects from every political party. So again, most of the time in outcomes research, we will get a convenient sample, but if at all possible, we want to do randomized sampling, or one of the methods that we've just talked about, so that when we look at that p-value, we know that it is legitimate. A study might be statistically significant, and perhaps we've done all of our homework. We have randomized a large sample or sufficient sample number so that it's powered, but maybe that result is clinically irrelevant. So I want to talk a little bit about the difference between statistical significance and clinical significance. Is the result that we get large enough to prompt a change in our clinical practices? Remember, just because a published paper presents a statistically significant result doesn't mean it necessarily has a biologically meaningful effect. We go back to our princess and the p-value. Let's say that he had enrolled 60 subjects and he really did see a difference after introducing a third group, a third comparison group. Perhaps the effect overall is not enough to have everyone in the kingdom drinking gallons and gallons of grape juice. The results of a large study may produce statistically significant results, and yet the deviation from the null hypothesis may be too small to be of any clinical interest. Let's say that we've conducted a pain medicine study. Our p-value was 0.03. But remember, that significance does not measure the size of the difference. It only tells us how different our finding is from the larger unknown population. The pain is reduced, but perhaps only by a small amount. Did the study account for degree of pain reduction, or just a yes and no answer, the pain was reduced? On the other hand, a study with a small sample size finds that a treatment was very effective, but due to the small sample size, the results do not reach statistical significance. The study needs to be repeated with a larger sample size, or perhaps combined in what we call a meta-analysis. Let me give you an example. Let's say that we work for a large pharmaceutical company and we are testing a medication that blocks phenylalanine absorption in people who have PKU. Phenylketonuria, or PKU, is a rare order of metabolism affecting 1 out of 200,000 babies born in the United States. The disease is so rare that there are few people in our trial in our little metabolic center. So what we do is contact all the metabolic clinics across the country, and we do that same study and combine our results in a meta-analysis, and we see if the results really stand up under adequately powered studies. So, we can never be 100% sure of our results. There may be factors that impact our results. Remember my comrade in graduate school who tested the absorbability of 2 chemical versions of the same vitamin in rats? He found no difference in the blood samples of the control or the experimental group, and he accepted his null. When he sacrificed the rats at the end of the study, he found that the experimental group had tapeworms. A valuable lesson learned before he had to repeat his study. Give all the lab rats a worm treatment. We develop a research question, but we test the null, and then we look for a legitimate reason to reject it. Since we can't be 100% sure that we've correctly rejected a null, we select a level of risk we're willing to take that we might be wrong, typically 5% or a 1 in 20 chance that our results did not occur by chance alone. Remember, a type 1 error is when we reject the null when it's true. We think our results are significant when truly they're not. A type 1 error is also known as alpha. It can be one-tailed, as in a directional hypothesis, or two-tailed, a non-directional hypothesis. These can be set at 0.1, 0.05, or 0.01. A type 2 error is when we fail to reject a null when it's really true. We think our results are not significant, but they are. A type 2 error is called beta and is equal to 1 minus alpha. An increased sample size reduces a type 2 error. So we can have a false positive or a false negative. Power is the probability of detecting an effect given that the effect is really there. In other words, it's the probability of rejecting the null hypothesis when it is in fact false. When we conduct inferential statistical tests, we are testing assumptions. Every inferential statistical test has assumptions the data must meet in order to use and report the findings of the test results. We assume the null is true, and then we look for reasons to reject it. A primary reason for conducting descriptive statistics, as we've learned to do, is to determine if we meet the assumptions required to support the use of a particular inferential test. We assume the data are normally distributed. This is where descriptives are most needed. If the data are not normally distributed, we may not be able to use the more robust statistical tests, also known as parametric tests. If we do use the more robust tests and we violated assumptions, our results are not valid. Again, we go back to the princess and the p-value. When making comparisons between different groups, the variances of both groups must be relatively equal. This is called a test of homoscedasticity. If assumptions cannot be met, we must use the less robust non-parametric test to test our null and report our findings. Remember all those terms you've been mastering this semester, like normal distribution, independent, dependent variable, correlation, continuous versus non-continuous, variances, parametric, non-parametric, levels of measurement. It's all coming together. Knowing these terms will help you use a decision tree like the one above to select the correct inferential test of a null hypothesis. Hang on, because you're going to be using decision trees like this one as we progress further into inferential statistics. So once we have conducted our descriptive tests, where we've looked at the continuous and the categorical data, we can now use decision trees to conduct or select the right statistic, and that would be Z and ZT test, ANOVA, regression, Pearson product for correlation to look at continuous data, and then categorical data. We would pick these types of tests illustrated on your slide to make inferential tests of our sample and see how this relates to the larger population. We've also looked at sampling distribution, where we look at the values of a test statistic and see where it lies along our sample. So let's practice. Statistical data are only meaningful when we can apply them in some quantitative context. So let's say that a patient has a pulse rate of 58 beats per minute, but the implication of that number is only evident if we know where that score falls in relationship to a distribution of normal sample of pulse rates. A Z-score helps us translate a raw score into meaningful data by normalizing the score to a group. We know that the mean is 68 and the standard deviation is 10, and we know that our patient with a pulse is a pulse of 58 is 1 standard deviation below the mean. Scores expressed in terms of standard deviation is called a Z-score. In this example, a Z-score was -1. A pulse of 88 would have a Z-score of +2, or 2 standard deviations above the mean. We calculate this with an equation that we have introduced to you previously. The mean of a distribution of standardized scores will always be equal to 0 because the normal curve is symmetrical on either side of the mean. So again, you had some practice doing this in topic 2. If we want to know what percentage of our sample has a pulse rate above 50, we first determine the Z-score. We find the area under the curve, and we use table B1 to show us that area. We add the other half of the distribution to the number, because you really can't have a negative pulse rate, and the area for all scores above 50 beats per minute is 96.41%. So 96.41% of the population has a higher BPM than this individual. The other way to report this is percentile rank. When a Z-score is negative, as in this case, we subtract that percentile from 50. So for a Z-score of -1.8, 46.4% of the curve falls between the mean and a Z-score of -1.8, and so this fellow ranks 3.5% in the whole data set. He has a very low heart rate. We can also use SPSS to calculate a z-score. Let me show you how to do this. Grab a pencil and piece of paper, and we will go to SPSS and show you how this works. When using SPSS to calculate a z-score, it's quite simple. You go to Analyze, Descriptives, and Descriptives. In this case, we're going to take a calculated BMI in our sample and see how the kids rate to each other in this particular data set. So we'll move calculated BMI into the variable box. Click Options. We want to make sure that we get rid of minimum and maximum. We don't need it, but we will need the mean and the standard deviation to calculate a z-score. Make sure that you click this box. We want to save those standardized values as a variable in our data set. And we click OK. This is going to give us the z-score. And you can see it's running descriptives down here in the bottom, so we have to wait just a minute. And here we have calculated BMI. And we know that it's running it. So let's shrink this and go back to our variable view, and we see that we've added another variable to the entire data set of 315 kids, a z-score for BMI. If we go to data view and we scroll across, we can see that a z-score for BMI has been calculated for every child. Now remember, close to 1 would be close to the mean or average, and we see we have some kids here who have some pretty big z-scores, would deviate from the normal, but it's calculated for every child in the group. So that's pretty neat. Now let's compare a single score to our sample. Go to Analyze, Descriptives, and we're going to move this new variable into the box. This time we don't want to save a z-score of a z-score, so we click OK. And we see it's running the descriptives, and it says it's ready. Before we X out of this output box, I want to mention something that your book pointed out. The mean of all z-scores in a sample has to be 0, and there's always one standard deviation. That's just really the definition of z-score. So if we shrink the output box and can go back and see that we have our z-scores for every subject. So that's how this works. We now can select any child and know how that z-score fits into the entire sample. Let's talk about confidence interval. We mentioned that in topic 2 as well. It's a range of scores with a specific boundary or confidence limits that should contain our population mean. The wider the interval, the more confident we are the true population mean will fall within it. 2 z-scores in particular are used to calculate confidence intervals. A z of 1.96, which is 2 standard deviations above or below the mean, and a z of 2.58, which corresponds to 3 standard deviations above or below the mean. And if you remember from topic 2, this is how we calculate a confidence interval. But let's use SPSS to help us calculate a confidence interval. So let's go back to our data set and go to data view, variable view rather, and we select Analyze and Descriptives and Explore. And this time we're going to look at height in inches, so we would move that over to the dependent list. And then under the statistics, we would make sure it's set to 95%. And usually it's set to both, but this time you want to click this radio button. We don't need graphs and all of that, so we select OK. And scroll down, and there we have it. Our confidence intervals 48.18 to 49.01. So we're the 95% confident that our sample mean for height will fall between these two limits in the larger population mean. So that's how to calculate confidence intervals using SPSS. Now we're going to move into the one sample Z-test. A Z-score is where we compare a single individual data point to our sample. But if we want to compare the mean of our sample to the whole unknown population, we use a Z-test. We're comparing a sample statistic to a population parameter. The Z-test represents the distance between a sample mean and the population mean divided by the standard error of the mean. So again, a Z-test is used when we are looking for differences between a sample mean for a particular variable in one group and the whole population. The question answered is, does the sample mean belong in the large population? Let's say we want to know if children born prematurely have a lower IQ than children who were born full term. We randomly select, and now you know how to do that because we saw a random number table used earlier. We randomly select 30 children who are 3 years old, who we know their birth history, they were born at 30 weeks. Our research tells us, because we've done a lit search, that the average IQ of 3-year-olds born at full term is 105. So we write a statement of null and research hypothesis. We hypothesize there's no difference in the mean IQ of premature and full-term children at age 3, or our research is there is a difference in the mean IQ of premature and full-term children at age 3. We set our alpha priori level at 0.05. We select the appropriate test statistic, and I've given that away because we're learning about Z-tests. And then we compute that test statistic, also known as the obtained value, and compare it to a table. So we have to compute our standard error of the mean, and then we get our Z-score. Now our Z-test for the sample of children who were premature comes out at 1.72. Is this significant? Is a 5-point difference between these two groups really meaningful? We determined the value needed to reject the null using the table of critical values for the Z-test statistic. This is a non-directional test, so our sample mean could be on either side of the normal curve. So we will divide 0.05 by 2. Our sample mean could fall in either extreme of the normal curve. We know the critical value associated with our alpha priori level of 0.025 is a z-value of 1.96. Said another way, we know that 95% of the area under the curve is bounded by z equal 1.96. Therefore, there's a 95% chance that a sample from this population will have a mean within these boundaries. This means there's only a 5% chance that any sample mean from the whole population would fall beyond 1.96 on the curve on either end. The tails of the curve beyond 1.96 represent the critical region or region of rejection of the null. The score associated with 1.96 is the critical value. So we compare our obtained value z equal 1.72 to the critical value, and we make a decision. Since our obtained value is less than the critical value, we accept the null, and we report the result as The mean IQ of premature children is not different from IQ of children born full term at 3 years of age. Z equal 1.72, P is greater than 0.05. And we can illustrate these results. You see that 1.72 score of the sample falls within this rejection region. What if a review of literature suggests that the mean IQ of premature infants is higher than children born full term when both are tested at 3 years? We have sufficient evidence to make a one-tail test of significance. Now we can use a more robust test. When we have a one-tail test, the mean IQ of premature children is not greater than 100, or our research hypothesis, the mean IQ of premature children is greater than 100. We know the critical value associated with P equal 0.5 is 1.65. Any obtained value greater than 1.65 is significant. Our Z test statistic obtained value was 1.72, which is greater than 1.65, so we fail to reject the null. The IQs of premature children in our sample is now tested, and it's not significantly different. And that concludes this lecture.